Hello everyone, welcome to the discussion of exercise questions of chapter 14, that is wave, of class 11 NCERT physics. So the first question says that explain why or how in a sound wave the displacement node is a pressure antinode and vice versa. So the complete question is, in a sound wave the displacement node is a pressure antinode and the pressure node is a displacement antinode and vice versa. So here we know that sound waves are longitudinal waves, meaning the particle of the medium oscillate back and forth in the direction of the wave's propagation. These waves consist of compression and rarefactions, and displacement node is the point in the medium where there is no movement of particles, or we can say zero displacement of particles. And pressure antinode is the point where there is a maximum variation in pressure. So in a sound wave, when particles do not move, the displacement node, the pressure is at its maximum or minimum. This happens because the compression and rarefaction of air is greatest when the particles are not moving. That is, they are either compressed or they are expanded the most. Conversely, when the particles move the most, displacement antinode, the pressure variation is minimal. Pressure node. Because the particle move away from high pressure areas towards low pressure areas, that's why the pressure minimizes. Thus the displacement node corresponds to the pressure antinode and displacement antinode corresponds to the pressure node. Now the second question we have, how do bats ascertain distances, directions, nature and size of the obstacles without any eyes? So we know that bats don't have eyes, so they use this biological process of echolocation to navigate and hunt in the dark, and they can infer or analyze the reflected sound waves for distance, direction and nature and size of objects. For example, so for distance, what they do is that based on the time delay between the emission of the sound and return of the echo, they calculate, their mind signals the distance, and for direction, what they do is the difference between the time and intensities of the echo, they detect the direction. And for the nature and size of object, by analyzing the quality of echo such as the frequency shifts, and so these provide the information about nature and size of the object. Now the third question is, why can we distinguish between a violin note and a sitar note even if they have the same frequency? So the ability to distinguish between the different musical instruments playing the same note is due to the concept known as timbre or tone color. So what happens is that the sound produced by any musical instrument is not just a pure tone but a complex mixture of the fundamental frequency. So there might be difference in the prominent frequency, like which frequency is getting higher, the frequency mix is getting higher, and which is getting lower for the different instruments. The violin and sitar have different body structures, materials and the mode of vibration, which produces unique set of harmonics along with the fundamental frequency. The distinct combination and intensity of these harmonics or overtones give each instrument its characteristic sound, or what we call it as a tone color, allowing us to distinguish between them even when they play at the same note. So fourth question is, why can solids support both longitudinal and transverse wave but gases can only support longitudinal wave? So in this question, the gaseous particles are not rigidly connected, so they can only support oscillations when the particle move back and forth, that we term as longitudinal wave. And there is also no restoring force or very less restoring force available for the gas particles to support the transverse oscillation. So that's why transverse waves can't travel in gaseous media. Now the fifth question is, why does the shape of pulse gets distorted during propagation in dispersive media? So let us first know what is a dispersive media. So dispersive media is a media where the wave speed depends on the frequency of the wave. So in dispersive media, because different frequency components of the pulse travel at different speeds, The pulse shape changes over time, and higher frequency components might travel faster or slower than the lower frequencies, causing parts of the wave to spread out or compress. This effect causes the original pulse shape to distort as it propagates, leading to smearing or spreading out of the pulse over time. Let's move to the next question. The question says that two sitar strings A and B playing the note Ga are slightly out of tune and produces beats of frequency 6 Hz. The tension in the string A is slightly reduced and the beat frequency is found to reduce to 3 Hz. If the original frequency of A is 324 Hz, what is the frequency of B? So let us first know what is the beat. Beat is when two sound waves of slightly different frequencies interfere with each other, they produce the phenomena known as beats. Now we have been given two strings, that is A and B. They are slightly out of there is a beat between them, so we have been given that they both are playing same note Ga with a beat frequency of 6 Hz. So it says that the difference in their frequency is 6 Hz initially, and in the second case what happens is that tension in the string A is slightly reduced, so the beat frequency also changes to 3 Hz. So we have to find out original frequency of B. So we have two unknowns over here, and we have two equations. So let us approach this problem. In the first case, we have been given that beat frequency is 6 Hz and the frequency of B is 330 Hz. So by the definition of beat, we can say that the initial frequency of A is 324 Hz as given, and the frequency of B is 330 Hz. So if A dash will be equal to 327 Hz. So let FA be the original frequency of string A, and so FA we can calculate based on the beat frequency, that is 324 Hz. And FB is the frequency of string B. The initial beat frequency is 6 Hz, so FB would be equal to either 330 Hz or 318 Hz. So now let us consider both the cases. First we will calculate with FB equals to 330 Hz, and then we will calculate with FB equal to 318 Hz. So when we calculate FB equal to 330 Hz, then we see that F dash A equals to 324 Hz, and in the second case we get F1 dash as 315 Hz. So F1 dash is 315 Hz is more possible because with decrease in tension the frequency will also decrease. So FB is going to be equal to 318 Hz. Now let us move to the next question. In this question we have a pipe of 20 centimeter long is closed at one end. Which harmonic mode of the pipe is resonatingly excited by a 430 Hz source? Will the same source be in resonance with the pipe if both ends are open? So here key concepts are closed end pipes. A pipe closed at one end supports a standing wave with a node at the closest end and antinode at the open end. And the fundamental mode of such pipe is quarter of the wavelength, that is lambda by 4, fitting within the length of the pipe. Now for the open end pipe, both the ends support the antinodes, and the fundamental mode is the half wavelength, that is lambda by 2, fitting within the length of the pipe. And we also know that relationship between the speed, frequency and wavelength is speed of the wave is equals to frequency times the lambda or the wavelength. So let us consider first pipe closed at one end. So resonant frequency occurs at odd harmonics only, that is 2n minus 1 lambda by 4. The length of the pipe would be given as 2n minus 1 lambda by 4. Now calculating the wavelength would be equal to speed by frequency, and that will give us 0.707 meter. Now determining the harmonic mode, so we will equate it with this equation 2n minus 1 lambda by 4. So we will get as n equals to 1. So thus we know that the first harmonic or the fundamental mode is resonantly excited over here. Now for the pipe open at both ends, resonant frequency occurs at all the harmonics of the fundamental frequency. where the length of the pipe is given as n lambda by 2. Here lambda we know from the previous calculation that lambda is equals to 0.7907 and length is equals to 0.20 meter. So we will know the mode of vibration, that is n equals to 0.5. Now n must be an integer, so no resonance will occur for this frequency. So 14.16, the steel rod of 100 centimeter long is clamped in the middle. The fundamental frequency of longitudinal vibration of the rod is given to be 2.53 kilohertz. What is the speed of sound in steel? So here the steel rod is clamped in the middle. It means that middle part of the steel rod is having a node. So the wavelength of the fundamental frequency of the load clamped in the middle is given by lambda equals to 2L by n, where n is equals to 1. So lambda would be equal to 2L. Now speed of the wave would be, we know that speed of the wave is equals to lambda times wavelength times frequency. So substituting the value of lambda relating the length of the steel, we will get the speed of the wave as 5060 meter per second. Let's move to next question, that is 14.15. So here the question says that a meter long tube open at one end with a movable piston at other end shows resonance with a fixed frequency source, a tuning fork of frequency 340 Hz. When the tube length is 25.5 centimeter or 79.3 centimeter, estimate the speed of sound in the air at temperature of the experiment. The edge effects may be neglected. So here the length of the tube is meter, and it has a movable piston at the other end, and it shows a resonance at the fixed frequency source of 340 Hz at the tube length equals 25.5 centimeter or 79.3 centimeter. Now we have to estimate the speed of sound in air at the temperature of the experiment. So for resonance in a tube open at one end, since other end is having a piston over here, so we can say that L will be equal to 2n minus 1 lambda by 4. We also know that speed of the wave is given by frequency times its wavelength. So identifying the modes corresponding to the given length, it will be equal to n equal to 1, L1 would be equal to lambda by 4. Here lambda is equals to 1.02 meter. And now L2, since we are given L2 is equals to 79.3 centimeter, so which is similar to 3 times L1, which is similar to 3 times 25.5. So calculating the speed of sound, we will get the speed of sound as lambda times frequency. So we know from calculation that lambda is equals to 1.02 meter. Now it will be equal to 346.8 centimeter per second. Let's move to the next question. So in this question, it is given that a wire stretched between two rigid supports vibrates in its fundamental mode with a frequency of 45 Hz. The mass of the wire is 3.5 into 10 to the power minus 2 kg and the linear density is 4 into 10 to the power minus 2 kg per meter. What is the speed of transverse wave on the string and the tension in the string? So we know that speed wave on the string is given as by the formula under root T by mu, where mu is the linear mass density and T is the tension. Now frequency of vibration in the fundamental mode would be given by V by 2L, where L is the length of the string and V is the speed. So here we have to find out speed of the transverse wave and the tension. T we have to find out T here and V here. So we know that frequency is 45 Hz in the fundamental mode. So the mass of the wire would be equal to, mass of the wire is given as 3.5 into 10 to the power minus 2 kg, and also linear mass density we can calculate as 4.2 into 10 to the power minus 2 kg per meter as it is given. So we first calculate the speed of transverse wave. So speed of transverse wave is given as lambda times frequency, and lambda we can calculate from here, and that is 2L times frequency. So the speed of transverse wave would be equal to 78.75 meter per second, and tension in the string would be equal to under root, we will equate the speed of the transverse wave with the with this relation, that is the speed is equals to under root t by mu, where mu is the linear mass density. Now we will get the value of t as tension as 248 Newton. Moving to the next question, we have given below are some function of x and t to represent the displacement transverse or longitudinal wave of an elastic nature. State which of this represents a traveling wave, stationary wave, or none at all. So we know that the traveling wave is represented by this type of relation, that is y as a function of x and t, where it is a function of x plus minus vt, and the stationary wave is given in the form of y xt equals to a cos kx into b sin omega t. Now in the first relation we can see that it resembles the stationary wave form, so we can say that it is a stationary wave equation. And the second form doesn't represent any wave form, so we can easily say that it is not at all a wave equation. And the third function is y equals to 3 sin 5x minus 0.5t plus 4 cos 5x minus 0.5t. So it is in the form of it is having same phase, so we can use trigonometric identity to make it resemble like the first equation of traveling wave, so we can say that it is a traveling wave. And the fourth option is y equals to cos x sin t plus cos 2x sin 2t. So again it represents the form of a stationary wave. We can transform cos 2x sin 2t in the form of cos x sin t, and we can simplify it to this form of a stationary wave, so we can say that it is a stationary wave. Let's move to the next question. So the question says that for a wave on a string described in exercise 15.111, do all the points on the string oscillate with the same frequency, phase, amplitude? Explain your answer. What is the amplitude of a point 0.375 meter away from the one end? So this exercise 15.11 15th resembles the previous version of the previous version of the book, in which it was termed as 15th chapter. So let us first revisit the question number 11. It says that a transverse displacement of a string clamped at both the ends is given by y is a function of xt y is a function of xt which is equals to 0.06 sine 2 pi by 3x cos 120 pi t, where x and y are in m and t in second, where x and y are in meters and t is in second. The length of the string is 1.5 meter and the mass is 3 into 10 to the power minus 2 kg. We have to answer, does the function represent a traveling wave or the stationary wave? So the given wave equation is in the form of y xt equals to a sin kx into cos omega t, and this represents a stationary wave, so we can say that it represents a stationary wave. Now the second question is, interpret the wave as a superposition of two waves traveling in opposite directions. What is the wavelength, frequency, and the speed of each wave? So using trigonometric identity, 2 sin a minus b plus sin a plus b equals to sin a cos b, we can easily bifurcate it into two equations. Notably, it would be like this: y xt equals to a by 2 sin kx minus omega t plus sin kx plus omega t, where k is the wave number and omega is the angular frequency. So as per the given wave equation, omega is equals to 120 pi radian per second and frequency is 60 hertz. Also k we can find out as 2 pi by 3, that is given. So the lambda would be equal to 3 meter. That is the wavelength. Now the third question is, determine tension in the string. We can use this formula for the speed of the wave in the string, that is given by under root tension divided by linear mass density. So here T is the tension, and we know the speed of the sound wave here, which is the product of wavelength times the frequency. So using this we can get the tension, and that would be equal to 648 Newton. Let's move to the next question. If you have any doubts, you can ask in the chat section. So for a traveling harmonic wave yxt, 2 cos 2 pi 10t minus 0.0080x plus 0.35, where x and y are in centimeter and t is in seconds. Calculate the phase difference between oscillatory motion of the 2 points separated by a distance of. So we have to find out the phase difference between oscillatory motion of the 2 points separated by a distance of. They are given. So here we have to find out phase difference with the given distance. So we know that phase difference is calculated by the formula of when the distance is given, when the partition distance is given, we calculate it with the multiplication of wave number with the distance of separation of distance. So here in the first option, the distance of separation is given as 4 meter. So and we also know the value of k, that is 0.008. So when we multiply it with that, we will get the phase difference. So using this formula, we can easily calculate this value. Now for the next question. It is given that for a wave described in exercise 14.8, plot the displacement y versus t graph for x equal to 0, 2 and 4 centimeter. What are the shapes of these graphs? In what aspect does the oscillatory motion in traveling wave differ from one point to another, amplitude, frequency or phase? So given this function of wave, we have to plot the yt function with the given value of x. So as we all know that this should be same function, so the frequency is going to be same and amplitude is also going to be same. Since we are pointing at different position in displacement, so we will get a different phase angle, as we can see in this all these three calculations. So phase, there will be only difference in the phase, that is in the first case we will get 36t plus 0.0785, and similarly we can calculate it for 2 and 4 as well, and we see that omega doesn't change and a also doesn't change, and that is the amplitude doesn't change. Now for the next question. It says that a transverse harmonic wave on a string is described by this function, where x and y is in centimeter and t is in seconds. The positive direction of x is from left to right. Is this a traveling wave or a stationary wave? If it is traveling wave, what is the speed and direction of its propagation? So traveling wave is given by this form, ya as a function of xt, where that is equal to a sine kx plus minus omega t plus phi, or it can be a function of cos as well. Similarly, second stationary wave is given as the 2a sine kx cos omega t plus phi. Now given a function here is of the form of traveling wave, so we can say that it is a traveling wave, and we have to find out amplitude and frequency. So amplitude is the coefficient of this sine or cosine function, so here it is 3, and since distance is given in centimeters, so the amplitude will be 3 centimeter, and the frequency is the coefficient of the t variable is the angular frequency, that is 2 pi by t, so we can easily calculate frequency with this, and the answer is 3.75 hertz, 3.73 hertz. Now the third question is, what is the initial phase at the origin, and what is the least distance between two consecutive crests of the wave? So least distance between two consecutive crests of the wave, it is signaling the distance, the wavelength. So we will have to find out wavelength here, and we have to find out initial phase at origin. So initial meaning that t is equals to 0, and origin means that x equals to 0. So when we substitute t and x equal to 0, then we will get a phase of pi by 4. So the phase would be equal to pi by 4, and the least distance, that is the wavelength, we can calculate the wavelength with the coefficient of x. K here represents the wave number, that is 2 pi by lambda, and when we equate 2 pi by lambda to 0.018, we will get the value of lambda, that is the wavelength. So it can be calculated from here. Moving to the next question, we have hospital uses an ultrasound scanner to locate tumors in a tissue. What is the wavelength of sound in the tissue in which the speed of sound is given, and operating frequency is given. So we can easily use the formula for speed of the wave, that is the the product of wavelength times frequency, and here frequency is given and also the speed is given. We have to find out wavelength, so we can easily divide the speed of the sound with frequency and we will get the wavelength. Moving to the next question, we have a bat emits ultrasonic sound of frequency 100 kilohertz in air. If the sound meets the water surface, what is the wavelength of the reflected sound, the transmitted sound, and the speed of the sound in air is 340 meter per second and in water is 1486 meter per second. So here two different speed of the sound is given. The one is of reflected that bounced back and got reflected in the air. So we will use the speed of the sound in both the media in order to calculate the wavelength in both the medias. Using the same formula, V equals to the speed is equals to wavelength times frequency. Here speed is given and frequency is given. We only need to find out the wavelength. The next question is, you have learned that the traveling wave in one dimension is represented by function y equals to fxt, where x and t must appear in the combination of x minus vt or x plus vt, that is y equals to f x plus minus vt. Is the converse true? Examine if the following function of y can possibly represent a traveling wave. So converse is not true. We know that for a function to be a wave function, the function must be single valued function, that is for every value of y there must be for every value of x there must be single value of y, and also for the function and its derivative must be continuous, that is there shouldn't be any discontinuity, or the function must not be undefined at any position. And the third requirement is del 2 y by dt2 must be equal to k del 2 y by dx2. So here we see that using this criteria we can easily find out which of them represents the wave equation. As converse is never true, it should follow these three conditions. So here let's move to the next question. The question says that use the formula V equals to gamma P by rho to explain the speed of the sound in air is independent of the pressure, increases with temperature and increases with humidity. So here we have been given the speed of sound in air, and we have to show that it is independent of pressure, but there is a pressure component. So we will try to nullify this pressure component and then we can show that it is independent of pressure. So here for ideal gas we know that pressure is equals to rho RT, and we can substitute here in the place of pressure we can write it as rho RT. So the equation, the formula will become under root gamma RT, which is independent of pressure. So it is the sound in air is independent of pressure, and with temperature it will increase because it is directly proportional to under root of temperature. So with increase in temperature it will increase with a factor of 1/2, and with increase in humidity, what happens when we increase humidity is that humidity actually refers to the amount of water vapor in the air. So air with higher humidity has more water molecules which are less massive, and then the nitrogen and oxygen molecules that primarily make up the air dry. When the air is humid, the average molecular mass of air is decreased. Since the density is related to the molecular mass of the gas, with the humid air being less dense than the dry air at same temperature and pressure, the speed of the sound increases. So it is inversely proportional to the density. Moving to the next question, we have a steel wire has a length of 12 meter and a mass of 2.10 kg. What should be the tension in the wire so that the speed of transverse wave on the wire equals the speed of sound in dry air at 20 degrees centigrade? So we know that the speed of sound in the string or in the wire is given as under root T by mu, where T is the tension and mu is the linear mass density. Linear mass density is the mass divided by length or mass per unit length. Here we have been given the speed of sound in dry air and we have to equate it to that of the string. given that unknown tension is there, and we have to find out the tension for which it will equal the speed of the sound in dry air. So here only one value is unknown, that is t. We haven't given the v. We know the value of mu, so we can easily find out t over here. Now the next question is, a stone dropped from the top of the tower of height 300 meters splashes into water of a pond near the base of the tower. When the splash is heard at drop, given the speed of the sound in air is 340 meters per second. So we have to find out right after the stone is dropped from the top, after how much time will the splash of the water be heard. So the time will be the time of splash. Hearing the splash will constitute two time intervals. The first is the time taken by the stone to reach the pond, and the second the time taken by the sound wave to reach the top of the tower. So using the equation of motion, we can get time duration for needed by a stone to reach the base or the pond, and using the speed of the sound and given distance, we can calculate the time taken by sound wave to reach the top of the tower. So we can simply add them and find out the total time. The next question is, a string of mass 2.50 kg is under a tension of 200 Newton. The length of the stretched string is 20 meter. If the transverse jerk is struck at one end of the string, how long does the disturbance take to reach to the other end? We have been given the length of the string here, and it is just asking the time duration for this disturbance to reach the other end, given the tension, and the linear mass density is also hinted over here as the mass is given and the length of the string is given. So we can easily calculate the linear mass density. So we can easily use this formula to find out speed of the sound wave over there, speed of the jerk over there, and then we will calculate, we will divide it with the distance, and we will find the time, that is 0.5 second. If you have any doubt, you can simply ask any question. I will leave the chat open for a few minutes.